Hi everyone, and thanks for the kind introduction. As was mentioned, I'm the chief scientist and co-founder over at Lead Genius. We're a technology company based in Berkeley. Today I'll be telling you a little bit about how some of our internal technology operations work, in particular how we've built our core engine for data collection, data curation, and making data predictions. And specifically I'm going to talk about how this works in the context of sales. So my own background is in mathematics and in theoretical computer science. So moving into the sales domain was really new for me. But it turns out that a lot of what we're doing today in the sales universe is a problem space that is really interesting from a technical basis and has a lot of lessons from other domains as well. So let me start out by making a little bit of an audacious claim, which is that I think that in 10 years, the job of salespeople is going to be largely replaced by artificial intelligence. And this is a bold statement. What I mean by this isn't that we're going to fire all of our salespeople and put them out of work, but what I mean is that we're going to have a system that is more like the systems that we've seen take place through mechanization of other fields, where you have a lot of people who are still in operation but wielding a set of very sophisticated technology tools that make their jobs easier. So you'll have a few people who are pulling the levers in a big operation for sales, and they'll be assisted by a whole lot of software. Some of that software is software that we're building at Lead Genius. But for those of us who aren't in sales, I don't come from a sales background either, it might be useful to briefly talk about what salespeople do all day. So what do salespeople do all day? Well, salespeople find companies or people who might want to buy something. The old school way was they would have a Rolodex, they flip through it. The new school way is that they might browse through LinkedIn, go person by person, check each one of these people's profile and see if they want to buy something or not. They might think a little bit about each one of those companies and try and decide if they want to buy what their company is selling. The old school way was a system called BANT, which is see if they have the budget, the authority, the need of the time. The new school way is you use some advanced tools like HubSpot that do a little bit of behavior analysis to try and see if somebody is really engaging in your product or service. And then they actually go through and sell to those people, and that's through the form of one-on-one outbound communication and outreach. Old school way was you'd call them up, you'd work your way down the list, say, hey, do you want to buy something? No, sorry. Hey, do you want to buy something? Yes, great. The new school way is people who are sitting at laptops all day, typing away, sending emails, trying to figure out if people want to talk to them or not. So I think about these as three technical problems. One is a search problem, one is an intent problem, and one is an actual natural language communication problem. And we call this the search problem, the intent problem, the sales problem over at Lead Genius. So our goal as a company is to build out software that addresses each one of these points in turn. So we're building AI that finds companies, AI that tries to understand buying behavior, and AI that actually talks to people. Let's talk about each one of these problems in turn. We'll start out with building AI that searches for customers, the actual search problem. So the way we think about this problem is this. A customer might come to us and say, well, we have a product. We want to know every single company in the world who might want to buy this product. Can you give us a list of those companies? That's a very hard problem. We'll start out by solving a slightly different problem, which is how we can just come up with a database of every company in the US, and then we'll look at how we can filter that down to companies that might be a match for a particular customer's products. Okay? So the easy way is to start out with a data pipeline. The way we've done it is by crawling data for about 55 different sources. Start out with a whole bunch of business directories online. We've also used a few of the public APIs like AngelList. We've plugged into all the Secretary of State databases. Some of these are not neatly accessible. Some of them are providing you free information, but they don't really make it very simple for you to crawl government data. And sometimes they'll just send you a CD. There's also SEC filings, and then there's lots of public records that are easy to access, like the IRS nonprofit database. And in our system, our pipeline is set up with Scrapy and Beautiful Soup, running on a virtual machine cluster. We can take web pages, raw web pages that have lots of information in them and take them apart. It takes a human being a little bit of time to set up the parsing structure and deconstruct it, but once you've done it, you can run the schema pretty easily. We're doing this on a pretty large cluster of machines. You can see that we've got various parameters that we're pulling straight out of the web pages. Pretty straightforward process. For information that is a little trickier to get, if sources are not very friendly to obtaining information, for example, for those Secretary of State web pages, you'll find that they're built in frameworks that are not really amenable to crawling. We've used tools like Sakuli and Selenium to simulate browsers to actually grab the information. It's relatively happy because it's brittle depending on the page structure, but it actually works very well. And you can grab information pretty reliably from those systems. Okay, so here's an example of how efficient this is in practice. We're running a compute cluster of virtual machines on Windows Azure to pull about 7.5 million companies, which is what we found in one particular state's database. We could grab all the information, process it, and link it into our directories in about half a second per organization. Takes about 43 compute days or $50 in virtual machine time. And that pulled out 202 gigabytes of data. So pretty efficient, pretty effective. The data, once it comes out, looks like this. We're running a linking process behind the scenes to match these companies up with one another. But you can see it's basically firmographic data, right? Things about the company, the web domain, the organization size, the revenue, etc. And this is a compilation from different sources. So we pulled information that wasn't just in one particular record, but found in multiple sources. So it's difficult to get, say, the organization size just by looking at the, say, the Secretary of State database record. But it would be easy to get the organization size by looking at the company's About Us page. So we grab information from both those sources and combine them behind the scenes. Okay, that's a tricky problem. There are lots and lots of companies inside all the different sources we might look like that have very similar looking names or otherwise might be similar in the various parameters that they have. So for example, you can see here on the right some of the companies in our database that have very similar names. Ortho is a very common term. It's used in lots and lots of different data sources and lots of different data sources to refer to very many different companies. It's a tricky question to ask if two companies that have a common name like Family Dental or Family Ortho are the same company or different companies. So here's a problem. You can think about how you might solve this. How do you tell if two companies that are being talked about on different places on the web are the same company or different companies? So another problem that comes up often is that companies change their names. Sometimes those name changes are cosmetic. They've just changed the name from one name to another, but the company, the entity, the legal structure are all the same. Sometimes companies have established subsidiary relationships with other companies. So they're actually forking themselves off into two different companies that are no longer the same entity. And that makes things very tricky. When you're trying to figure out if web content refers to the same company or different companies, you have to figure out very quickly if these companies are the same or different. So here's how we did it. I'll give you two solutions. The first is the fancy way. The fancy way is to turn a company, P, into a vector of 30 different properties that we know about it. And these properties are different properties that we're able to pull from the company's record in the particular source that we looked at. So for example, from a company's website, we want to be able to pull their name, their address, their industry, the founding year, and the technologies they're using. From the Secretary of State database, we may find information about the organization's name and address, their revenue, and their industry. We turn all of these objects into vectors in feature space, third-dimensional feature space. You can add or remove features as desired to get a smaller or bigger vector space. And then you just run a nearest neighbor algorithm on these. And the probability of two companies described in different places being the same is dependent on this formula here, which is just the distance that they are in this feature space. And that's it. It's a straightforward approach, although you have to run it over a very large number of companies. The distance between any two companies is the probability that they are the same company. Okay? So you can decide if two companies are the same by drawing a little circle around two companies in that feature space and deciding if they are in the same circle, if the distance between them is small enough, then they're the same company. And if the distance is big, then they're probably different companies. And deciding what that value of epsilon is tricky, and we obtained it experimentally by running this over enough examples and labeling all the mistakes and getting it to be small enough that it actually worked. Okay, and so here's what that actually looks like when you run it. You end up with a whole bunch of probabilities and outcomes for different companies. Okay, so this works. It's pretty slow. It requires us to do a lot of pairwise comparisons around a huge number of data points and data sources. You can optimize this. We did optimize it. Data falls out of date constantly, so we have to rerun it quite often. And when you optimize it, you can reduce the number of comparisons to being substantially less than n squared. But you still have to do a fairly large amount of compute-intensive work. There's a shortcut you can apply. If you saw the last talk, you might have an idea of what it was. There's an easier way to solve this, which is to look at the small number of parameters that are hugely predictive and less likely to change. And there are features that do that. The easy way is to use the USPS standardized address for the headquarters of the company. This works in a lot of cases. And if you standardize the format to a normalized format given by the USPS, that one parameter is actually hugely predictive about the identity of the company. Companies may change their location, but they tend to change it across all of their listed official registrations. Okay? And you can use a simple heuristic like this. Two companies are the same if and only if they have the same official physical address. Okay? So one thing you might think about, and I'll leave this one up as a question to the audience, all the answer is not tricky. What do you do if this company moves? How do you update your records efficiently and effectively? Okay. Great. So, of course, we've done this crawl. We analyzed this over the entire U.S. We came up with about 21,700,000 businesses in the United States. It's not too far off from the official U.S. Census readings. About 6 million of those are what we call interesting companies. And by interesting, we mean that they have more than one person working in there. I put up some comparables here about how other sites have listed the number of companies that they track. Yelp's got about 47 million establishments, so physical locations. Some of those are the same legal entities, some of those are different. LinkedIn's only got about 2 million unique companies. Crunchbase, 650K. It's gone up since this talk was put together. AngelList's got about 300K. Same story, it's gone up. We can answer some interesting questions using this data. Here's one example. Which U.S. industries have the most distinct organizations? When I say industry, I mean, say, retail or finance, based on the LinkedIn self-identified parameter. The answer is construction. You can see some of the numbers here. Number 2 is real estate. Those are the largest number of different organizations that are reporting themselves. Another question you can ask, how many Fortune 500 companies have websites? Answer is not 500, it's actually 499. And I'll leave that as an exercise to the audience, or come ask me afterwards if you want to find out which one that is. It doesn't have one. Okay, there's a bunch of bonus problems I won't go into, but I think these are really interesting, and I'd love to talk about them if we have more time. Understanding how long this information changes, how long it's accurate. You can model that with decay functions in your data and grab data selectively when it gets better. You can optimize the frequency by which you retrieve information using some expectation maximization algorithms. And then we have a great way to grab information from sites that don't have clean schemas just by watching humans do it and learning what the schema is through an inference method. But we'll come back to that another time. Okay. I'll talk very briefly about the intent problem. Building AI that understands buying behavior is a very big problem. We've taken a very small corner of this and started to address it. Basically, the problem is formalized like this. You come to me as a customer and say, I have this list of companies who have bought stuff from us in the past. Which company is going to buy from us in the future? Okay, so very tricky problem. It's not generalizable across industries very well. Whether somebody's buying something depends very heavily on the specific industry, and whether a company needs a product is always changing. So it's time dependent as well. Of course, one way you can solve this is with a classification algorithm. This is sort of the naive approach. Because we have all these companies that are already parameterized, we can pull in some of that data. If you've got about 10,000 customers, you can make a stab at this. You can train a neural network to do it. We've done this to see how well it works. You can learn a function to try and classify it, and try and decide if they fall into the category of going to buy now or not going to buy now. Okay, so you can do this to try and match whether companies are inside a buying profile or not. It works pretty well to know if a company matches a set of demographic parameters. It's hard to use that to actually predict if a sales outcome is going to happen or not. What we've done is this. We pull a probabilistic estimate on whether this company is going to be in market for a product or not. It's basically based on how similar that company is to companies that have already bought from the company in the past. If that probability is low, we escalate it to a human annotator who takes a call. And that call is just based on a similarity assessment that they're using informal parameters for. They can choose to add features to the model or propose features to the model. We review those manually to decide if those are good fits or not. And then we add that data to the training set. Now this is basically what a salesperson might do on a day-to-day basis. We've just taken this and given it to an annotator instead. And that boosts the likelihood of success to human levels, but only to the level of the human who's doing the labeling. So There's still more work to be done here, but you can do a little bit more that's more interesting. You can look at behavioral data. We've started to incorporate this, but we haven't taken most advantage of it yet. Behavioral data might include things like if they've looked at websites that are relevant to the technology that you're selling, if they've started hiring for roles that would use the technology that you're selling, if they've talked about this in social settings. All this information is in our database. We've yet to incorporate this into our prediction methods, but we have a feeling that there will be some significance to it in terms of deciding purchase decisions. Okay, the last thing I'll talk about is the last step that salespeople do, which is communication with people, which is building AI that talks to people. Now, actually building communication interfaces or chatbots is a tricky problem to cover all the bases, but if you're talking about this problem, there's a couple of advantages that we have. First of all, we're doing it over email. So we're talking about how you can sell people products or communicate with people about purchase decisions via email. So you're not time constrained. You can take as much time as you want to come up with an answer within reason. The second is that your conversation domain is highly constrained. You're only talking about, do you want to talk about buying this product, or are you not interested in this product? So you only have a limited number of things to choose from. Given that, we have a stab at passing it. So our challenge here is this. How do we write sales messages by email that are going to be as compelling or as good as those sent by a salesperson? Okay, so there's lots of plausibility arguments. If you look at results from deep learning, there's lots of great conversational systems that are solving way more difficult problems than this, right? So Xiaomi has done a whole bunch of good work on real-world chatbot scenarios. There's also been good support chat results trained on data. You can see lots of these and lots of great results. This is a nice support inquiry from Google. You can see that it's got a really nice natural language conversation that's happening in real time, much harder than what we're trying to solve. We break this problem down into two pieces. The first is writing a message. How do you compose the content? The second is how do you understand the response, classify it appropriately. Okay, so given the topic, an author, an inbox, and a recipient, we're trying to write a message that has a maximum likelihood of somebody writing back and saying, hey, yeah, I do want this. And it should look really plausible. It shouldn't look like it was written by a robot or by like a spam engine. It should actually sound like the author. And it should only be going to people, ideally, who actually want to receive this kind of message. It shouldn't just be going out to anybody. Okay, and we also have a couple of secret weapons in here because we have access in our systems to a set of data from our customers, which is their historical email conversations that they share with us to help bootstrap this system. And then, of course, we have a network of annotators that we can choose to use if we want to help annotate our information. Okay, so our approach is this. We craft a template based on analyzing the sender's email inbox and looking for things that look like outbound messages. We collect data at scale that we use to fill in the blanks, and then we customize that data based on all the stuff that we've crawled on the web. Okay? So here's an example of what that message looks like. Here's the template that we came up with. It's got a bunch of fill-in-the-blank spots, and the fill-in-the-blank spots are populated by information that we grab during our crawl. We've done a bunch of analysis about how likely people are to reply to us based on the length, the tone, the subject complexity, and the word choice. We optimized this a little bit. We've gotten some results I'll share here. Subject lengths that are longer, the subject is longer, people are less likely to open your email. If you include variables like your name, if you say, hey Joe, in the actual title of the email, the subject, they're much less likely to respond, which is a little bit counterintuitive, but if you think about it, you can understand why. It sounds very unnatural. And then of course, we published some work on this too, that you can use humans to try and edit those templates after you've generated them algorithmically to try and come up with good results. And we've got some publications on this if you want to take a look. Okay, the last problem is how to understand the responses, okay? We try and classify responses into 8 different types. People who are saying, yes, I'm interested, positive replies. People who are saying, I'm not the right person, but go talk to so-and-so. And then variations on, I'm not interested, like, I'm not interested, but talk to me in 6 months. Or I'm not interested and never talk to me again. We classify all of those. So we've done this via sentiment analysis. Sentiment analysis works pretty well. We were able to show that we can get pretty good results out of it, and then, as usual, you can escalate it up to a human as the easy way if your classifier fails, right? And then doing this, we've gotten a pretty robust label set that we've been able to use to train our overall system. You can take this further and script responses. I won't go into that in the interest of time. So that's it. We talked about 3 problems, searching for companies, companies that can understand buying behavior and intent, and software AI that can actually comprehend and hold email conversations. And we'll talk a little bit about how you can solve each of these problems in turn. that's it. If you'd like, we can take some questions, and please come talk to me. We're hiring. No, great. We'll have questions. Great. We'll take questions offline then.
Anand, thank you very much.